Today I'm going to be discussing the Coulomb's law. So what is Coulomb's law? So Coulomb's law is basically the electric force that is acting on the two charges. So we all know that um, opposites repel each other, right? So opposite charges, they repel each other. So the example here, if we do have two positively charged particle, they will repel each other. But if we do have a positive and a negative charge particle, they will attract. So opposite charges, they attracts. So to represent that force, so we have here is electric force. So this is the force, that's capital F, actually the electric force. Yeah, that is equals to the Q1. So let's start with Q1 first. This is the charge of the first particle, and the Q2 is the second charge of the electric charge. Okay, now, so the bottom, this is going to be the distance, and they are squared. So we're going to say this is the distance. So what does this K represents though? But before going to that, let's talk about charge even more. We already know that one photon is equals to 1.6 times 10 raised to the negative 19 coulombs of charge, and one electron is equals to negative 1.6 times 10 raised to the negative 19th coulombs of charge. So coulombs is basically the um, representation of the charge, the magnitude, the unit of charge. Okay, now, so what is this K? So the K is going to be the Coulomb's constant. So the Coulomb's constant is equals to the 1 over 4 pi epsilon naught, where epsilon naught is going to be the permittivity of this is the quantity of the epsilon naught, and this is the permittivity of free space. So this is a constant. It is equals to 8.85 times 10 raised to the negative 12 Coulomb divided by newtons multiplied by square meters. So that is the epsilon naught. So if we're going to plug in the permittivity of free space into that equation, we will get this. So the Coulomb's constant is equal to 9 times 10 raised to the 9 newtons multiplied by squared meters all over the Coulomb squared. So this should be Coulomb squared. Okay. So this is the Coulomb's law. Here, I'm gonna put arrow. So we have too much arrow though. Okay, now. Next up is their relation. So let me just put some force here. And let's put the electric charge here, Q, and the distance. Okay, so if the electric charge increase, the force will also increase. So if, for example, if the electric charge is massively big, then the force will increase. But if their distance is pretty much long, then the force is going to decrease. So to review of the electric charge, if we do have more proton than electron in an atom, then it is positively charged. So that's why we do have a positively charged particle, because there's more proton than electrons. So the reverse is true. If we have more electrons than protons, then the atom is going to be negatively charged. So that thing is going to be negatively charged. That's why we do have these things. But as the subatomic particle of proton and electron, they are always positive and negative. So 10 microcoulombs point charge is 35 centimeter away from negative 20 microcoulombs point charge. Calculate the magnitude of the electric force between them. So I did misspell the charge incorrectly, so we're going to replace it with the correct one. Okay, now, so this is the illustration. So what we're going to do here is just use the Coulomb's law to calculate the electric force that is acting between them. So They are opposite. We have a positively charged particle and a negatively charged electric charge here. Why do I keep saying particle? I mean, they are the same. Okay. So now we have force that is acting on this one. Okay, so how do we calculate it? First, we're going to use the Coulomb's law that we discussed earlier. So let's call this Q1 and Q2. So the first is equals to the this is force acting on 1 to 2 and 2 comma 1. They are the same. So force, we can just make it this capital F. So this is the Coulomb's law. So Coulomb's law, they are look alike with universal gravitational Newton's law. The force is equal to universal gravitational constant multiply the 2 mass and divided by the r squared, right? They're just almost the same. So we're just going to put some numbers here. Now let's use plug in the distance. So this is not going to be 35 centimeter, but we're going to convert this into meters. So we get this. We can cancel the centimeter. So now we have 0.35 meters squared. So I'm not going to put the unit. So there you have it. So I did put absolute notation on the numerator because we just want a positive answer. So the force that is acting between them is going to be 14.6 newtons. Actually 14.69 newtons. Sorry. Now let's move into this problem. You can pause the video, and this is just basic manipulation of equation. So we're just going to solve for r, which is the distance. So after some time, we finally have arrived it, and then we're going to plug in the givens. Okay, now so we're going to put this in our calculator. So this is taking too long. This is around 10.7 meters. Okay, so let's just write this. So there you have it. So that is the distance between them. Now let's move on to other problem. A force of 255 newtons exists between two identical points separated by a distance of 80 centimeters. Calculate the magnitude of the two charges. So now, I'm just use the Q sub 1 and Q sub 1 because in the problem it states that it is two identical point charges. So what we can do is just combine them. So we have this equation. This is going to be Q sub 1 and Q sub 1, all divided by the distance squared. So the force that is acting between these two identical electric charge is going to be Q squared. We can write it as that thing. So we have r squared here. Now we're going to manipulate this equation and solve for the electric charge. Okay. So now we can just divide both sides by the Coulomb's constant. So we have Fr for real, force times raised, distance squared. And now we can just cancel the radical sign. Okay, so now we have this equation for the electric charge. Okay, this is just basically simple manipulation. You can save this equation for notes or just manipulate the Coulomb's law. So force is going to be 225 newtons, and we're just going to convert 80 centimeter into meters because that's what we need. Okay, now we have this thing. We can just eliminate centimeters. We can also cancel some zeros. So we got 0.8 meters. We're gonna put it here. We're going to square it. Okay, and the Coulomb's constant is going to be 9 times times 10 raised to the 9th power. Okay, now we're just going to type this in our calculator, and the answer is going to be 0.00012. Okay, so we got this. We're just going to convert this into the scientific notation. So what we have is 1.265 times 10 raised to the negative 4, around negative 4 coulombs. Okay, so this is the electric charge of those identical point charge. How many electrons represents a charge of negative 140 microcoulombs? We're gonna put this here. So microcoulombs is just the same as times 10 raised to the negative 6. If you already studied the conversion process. So 1 electron is equals to negative 1.6 times 10 raised to the negative 19 coulombs. We can just cancel it here if we're going to use the conversion. Okay, we can just cancel the coulombs, and so the answer is going to be 8.75 times 10 raised to the 14 electrons. So this is how much electrons are present in negative 140. Now let's do this. What is the electric charge in microcoulombs of 5 times 10 raised to the 14 protons? So we do have 5 times 10 raised to the 14 protons, which is so many, right? It's around a quadrillion. So one proton, we all know that its electric charge, charge of one proton is going to be 1.6 times 10 raised to the negative 19 coulombs. So we can just put it in such a way that the protons will cancel. The unit protons will cancel. Okay, now we can just multiply this, type in our calculator. So the electric charge in microcoulombs of 5 times 10 raised to the 14 protons is going to be, this is too much. I'm going to convert this into microcoulombs. So we're going to go there 6. We're going to put the decimal on the right to the 6 of it. So we got 80. So 80 microcoulombs are present in 5 times 10 raised to the 14 protons. So we're going to recount it. We just move it. We just move the decimal into the 6 from the right to the right. Now let's try this problem. A metal sphere has 4.3 times 10 raised to the 21 protons and 6.8 times 10 raised to the 21 electrons. What is the net electric charge on this metal sphere? So we have a metal sphere here, and it contains those much of protons and electrons. So to calculate the electric charge, we have to know this equation. So the electric charge is basically the quantity of proton minus electrons multiplied by 1.6 times 10 raised to the negative 19 coulombs. So that should be negative 19. We're going to put it later. So we have this. We're just putting up what were given to us. Okay, now we can use our calculator, and don't forget that it is times 10 raised to the negative 19. I'm gonna put this. Okay, now let's just plug it in. So the net electric charge of this metal sphere is going to be negative 400 coulombs. So that's basically it. Save that equation. At 100 microcoulombs charge is placed at the origin, negative 50 microcoulombs charge is placed at x equals to 2 meters, and 200 microcoulombs is placed at x equals to 4 meter. What is the net electric charge acting on the 100 microcoulombs of charge? So we have a diagram here. We just draw it. So to calculate the electric charge, net electric charge that is acting on the 100 microcoulombs charge, we need to know its force. So if we're going to look on the first electric charge, we do have a force that is repelling, that repels the electric charge number 2. So we're going to call this F2 sub 1. That's the force that do repels it, right? Because electric charge, they do repel each other. So this is 2 over 1. So that's the force. And we also have a force that is acting on this 2, 3. And this force is attracts. It does attracts because opposite charge, they attract. So we have a positive 1 on the left and a negative 1 on the right. So this is force 2, 3. So now we all know the force. So this is unnecessary. I'm just going to delete it. So the force is, so the net force is going to be the force that is acting on between 2 and 1, which is the repelling force because they are opposite, plus the attractive force. So we have this. So the repelling force is helping the electric charge number 2 to go to the electric charge number 3. So this is just like a friend supporting you from your crush, right? Okay, so that's a unnecessary joke. Okay, now we can just plug in what we know. So the electric charge, net electric force. Wow, what is the net electric charge acting on the? That should be electric force, right? We just put this in this one. So I'm just going to put everything that we know on our equation and then use our calculator to calculate the electric force, that electric force. We have electric charge Q sub 2. It should be Q sub 2, not Q sub 1. Because we're not looking for the Q sub 1 and Q sub 3 forces. Okay, now let's type this in our calculator. So what is the net electric charge? So that is supposed to be what is the net electric force. So the net electric force that is acting is going to be 11.25 plus, so they are just the same though, so 11.25. So we're just going to take the sum of this, and the net electric force that is acting on the 100 microcoulombs of charge is going to be 22.5 newtons. So that's basically it for this video.